So I'm going to walk you through a Diels Alder reaction. This is going to be in several parts because it can be a little lengthy, but I'm going to first talk about in general what a Diels Alder reaction is and some of the key components. In the other videos, I'll show you why we get regioselectivity and why we get diastereoselectivity and in some cases stereospecificity. So looking at a general Diels Alder reaction, you need a diene, a conjugated diene, and you need a dienophile, which is just an alkene. It works best when your diene has an electron donating group and your dienophile has electron withdrawing group. Make sure you're familiar with what groups are withdrawing and what groups are donating. So right now I have my diene in the S trans conformation. That is because the single bond in the conjugated piece, you could see that those two double bonds are opposite of that bond line. So that is trans, but S trans in this case. It's not trans as in a cis and trans double bond. S trans is a conformational term. It's a rotation of that single bond. So S cis and S trans are the same compound, just different rotations. Think about drawing your Newman projections and rotating. You're not drawing a new structure, you're just rotating the position of the bonds. So that is S trans. Down here we have it in its S cis conformation. In order for a reaction to occur at Diels Alder, your diene needs to be able to move into the S cis. And you want to draw it in the S cis when you try to evaluate possible products, because that's going to help us determine, again, regioselectivity as well as diastereoselectivity. A standard Diels Alder reaction involves a diene reacting with the dienophile to give us a six-membered ring. So every Diels Alder will result in a six-membered ring in a double bond, at least one. Sometimes you'll have two double bonds if you start with a triple bond as your dienophile. What happens in a Diels Alder is the diene is more nucleophilic, it's going to give its electrons from the one pi bond to form a sigma bond. The dienophile is going to move its pi bond to the diene to form the second new sigma bond, and we're going to shift one of those pi bonds over, forming our pi bond in the product. So that is a standard Diels Alder. Again, because our diene is the nucleophilic piece, that's why we want donating groups on them. Because our dienophile is acting as the electrophile, we typically want withdrawing groups to kind of make it more electrophilic. So following that pattern, when I have my diene and my dienophile add together, if I were to look at this simply, what's going to happen is, and I'm going to draw it this way, we'll find that there's many ways we could have drawn it. We're going to get a product in which it looks something like this. Ignoring stereochemistry, I'm going to get this product. Now notice that my dienophile is trans. So that means in my product, my ketone and my methyl group need to be trans. So in all of my possible products shown, notice those two groups are always trans. The other thing you want to notice is what I like to refer to as the outside and inside of the diene. If we look at the diene and we kind of complete this circle, notice these methyl groups on the end. They are sitting outside of that circle or outside of the diene, the concave portion of the diene. They're sitting outside of that. So they're going to be the same. They're going to both be wedges or they're both going to be dashes in every scenario. Anything inside is going to be the same as well. Going back to our diene, you don't see them because you don't have to show hydrogens, but hydrogens are inside here. So all those hydrogens are going to be the same in every scenario. If my methyl groups are wedges, my hydrogens must have been dashes coming off of those carbons. We'll hit that in more detail when we talk about the endo-exo rule. So anyway, we have 8 potential products, and all of the products, based on our starting compounds, we need to have all of the methyl groups in these positions the same, either both dashes or both wedges, and these two groups always need to be trans. There are 8 different ways to draw that. And so we're going to figure out which are the major products. We will find that this one here, which is an endo product, is going to be our favorite product, and we will see why. It's also the regio selective product compared to having the carbonyl group up here. It's actually favored down here. And again, we'll see why when we look at regioselectivity. So I recommend watching the next videos to see why these two enantiomers here are the favored product. And if you have any questions, feel free to reach out by sending an email, and I can even make more videos that are similar.